Hi, my name is Rizvan Dirza. I'm a PhD candidate in the Department of Chemical Engineering at NTNU Norway. I'm working under the supervisions of Professor Sigurd Skogstad from NTNU and Dr. Dinesh Krishnamurthy, who is currently a postdoc in Harvard University. I started my PhD on February 2020. I have my master's degree in Systems and Control from Eindhoven University of Technology, the Netherlands. Before I started my PhD, I worked for around 6 years in several oil and gas companies. Today, I'm going to present one of our work entitled Optimal Resource Allocations in a Subsea Oil Production Network using what's called distributed feedback-based RTO approaches. This work is supported by SubPro, which is financed by the Research Council of Norway, major industry partners, and NTNU. I will give this presentation in a logical manner. I'm going to start with the reasoning why we decided to work on this topic and how we formulate the problems. After that, we're going to talk about the methodology that's possible to solve the problems. And before I show the implementation result, I will explain briefly the case study that we consider in this work. Finally, we will end the presentation with the conclusions. So in this work, I would like to emphasize that we apply a proposed method called DFRTO to a subsea oil production network. This method enables system-wide optimal performance using only simple feedback controller and selector, which is usually desirable by many operators or engineers in the field. This work is based on the background that the companies face in the recent years. For example, the location to produce hydrocarbon is getting more difficult nowadays. Many onshore fields has been dried out, the era of easy oil is over, people start searching oil in extreme locations such as the border field. To extract the hydrocarbon in that area, we need relatively huge investment that not every company has a lot of fund for it. Moreover, as the renewable energy technology resource is advancing, then other non-technical reasonings, hydrocarbon may not become the only energy resource or private provider anymore. This might contribute to volatile oil price that we experience in the recent years. It implies that we have more investment risk and operating risk in the economic aspect. And in order to manage the risk, we have to do something with these decisions or corporate actions. And what we can do fundamentally is by sharing the risk, which is actually a quite common way out for many big companies when they have to deal with a challenging oil field. Or for small company which does not have a lot of funding, for example, and quite lack of technical expertise and resources, they usually can put their participating interest and let other competent and more experienced companies to operate the production field. However, still, the small company may have interest and right in the field. The operator company should consider their interest in the operations. Thus, you are probably quite familiar with the term of joint operation, shared facilities, and resource allocations. To illustrate, in many cases, you can find shared facilities such as FPSO, as shown in the figure in the right-hand side of the slide, where hydrocarbon transported using subsea pipeline on the seabed and bring all the way up and mingles to these topside shared facilities, which is called FPSO. And as you can see, this hydrocarbon is coming from different subsea clusters that are owned by different companies, let's say A, B, C, D, and E, and its future tie-in cluster as well. In addition, the terms resource itself can refer to many things such as steam, power, raw material, or gas lift rate for a gas lifted oil production well. So again, as I mentioned in the title, the problem that you want to tackle in the business context is how to optimally allocate the resource in subsea oil production network. And in order to solve that problem, we need to formulate the problem properly, as we can see here, where we start formulating the problem as the optimal resource sharing problem, where we want to minimize the objective function of X by determining the optimal decision variables X. And this X can represent the allocation of the resources as well. We can also see here that we have N clusters, where each cluster has its own objective Fi, and the index I can be seen as the name of the clusters, Not also that here the xi is decision variables that is located in subsystem or cluster I. In large process system, you may want to decompose the entire system as a several local system, and then you can start optimizing the local system because it is practically easier to do. An interesting problem occurs when we have conflicting variables. As can be seen in equation 1b, we have a constraint function gx where we have shared constraints. In this formulation, we consider that we have limited total resources labeled by x bar. Thus, we can also say that we have shared resources. Typically, its local system will compete to get the resource to maximize its local objective, but it may not be good as an entire system. So we do not want this. So we want to find the optimal resource allocation such that we can minimize the objective functions. This is not an issue if we solve the problem integratedly or centralized way. The problem becomes interesting when we solve the problem locally, but we still want to achieve optimal performance as we can get when we solve the problem integratedly. Then we can also see this problem as a system-wide optimization problem. So the reasoning why we do this is because it is practically easier to optimize local system instead of doing that integratedly. And then in the context of joint operations, the local system or company does not want, probably does not want to share some of critical information due to several reasonings, for example, intellectual property or any other else. And so how do we solve this problem considering this requirement then? Then we propose several methods. Well, we do not propose, but we have several methods that can solve it. And the essential assumption that we need to consider in order to solve this problem is that we have additively separable objective functions. And then after we have that assumptions, then we can use several decomposition methods to solve the problems. Two decomposition method that we consider, that we can notify in many literature is primal decomposition and dual decompositions. We're going to talk about the primal decomposition briefly in this slide. As you probably see here, that primal decomposition has a local problem where each local system is trying to minimize its local objective given the auxiliary variable z. And the coordinator layers is responsible to ensure that the given allocated resource Z is providing optimal performance for the entire systems. And then these local and coordinated problems will be solved iteratively. The limitation of this method is that we need to know and share the local constraints, which might be costly or impossible for some cases. And it is also necessary to solve the numerical problems repetitively, which can be computationally intensive and may have numerical robustness issue. So alternatively, we can explore dual decomposition. First, we transform our primal problem into dual problem by obtaining Lagrange functions. That's why you may also heard the term of Lagrange decomposition instead of dual decompositions. They are technically the same. As can be seen, Lagrange function here is a function of decision variables and Lagrange multipliers. And if you see problem P, it is actually a problem that is a function of Lagrange multipliers. In economic interpretations, Lagrange multiplier is called shadow price. Again, they are technically the same, which is basically how much you need to pay to push your constraint. Since our objective is additively separable, and assuming that HI is equal to the average of total resources, our dual problem can be separated into several nice local problems that is actually unconstrained optimization problems. And we still need numerical solver to solve the problems. What about the coordinator problem? Similar to primal methods, we have similar form of coordination problems where we want to optimize the overall problem by determining the optimal shadow price to minimize the total values of the Lagrange functions. This is the total cost, then is the Lagrange functions. We can determine the optimal shadow price using subgradient method. As can be seen that the subgradient method, the subgradient itself is simply the coupling constraints Gx. And we do not need to know the local constraints as we have in primal decompositions. Then we can update the shadow price iteratively, where alpha is the step length. We can also see it as a controller where the shadow price is the dual manipulated variables that control the constraint function to 0. Note that here we consider inequality constraint in equation 1b. Thus, it is important to consider the KKT conditions, the complementary slackness and dual feasibility, where the shadow price is positive when the constraint is active and 0 when the constraint is not active. Therefore, we introduce a max selector. So at this step, the coordinator layer do not need to know any local constraints, and we do not need any numerical solver, and we can solve the coordinator problem using simple feedback controller and a max selector. However, we still need to solve local problem using numerical problem solver repetitively. That's why we here try to replace the local problems to simple feedback controllers. This is common. This is probably many traditional oil and gas company would like to do, because they also prefer to use simple feedback controller as opposed to model-based RTO. So in this work, we want to replace the solver with feedback controllers and introduce this scheme as distributed feedback-based RTO. Here, the key idea is to convert the Lagrange decomposition framework into feedback control problem by taking into account the KKT stationary conditions of different local problems. We need to control the gradient of the Lagrange functions in each local problem to be equal to 0. And for non-decomposition framework, we need to drive a vector of the gradient of Lagrange function to 0, 2. Based on this idea, we propose an optimizing control variable for each subproblem, and we call it as self-optimizing control variables. By controlling this gradient of Lagrange function to 0 using simple PID controller, then we purely have eliminated the need for numerical solver in this scheme. Thus, can strike out these limitations. To conclude this section, this figure illustrates the proposed method. As we can see, that the constraint is controlled by a central constraint controller or in the coordinator layer by updating the shadow price. Then we distribute the shadow price to each local system to be used to estimate the gradient of Lagrange function, the local one. Then we use local or inner controllers to control this gradient to 0 by updating the decision variables xi, and use this xi to the real process. As an additional information, we assume that we can estimate the gradient in this framework either by model-based or model-free approach. Now let's talk about the case study. We then demonstrate the proposed method in the case where we consider a large-scale gas lift oil production network with 10 wells producing well from 4 different clusters. Gas lift is considerably common and cheap artificial technology where compressed gas are injected to the well tubing via the annulus. By doing that, we expect that we can reduce the fluid mixture density and reduce the hydrostatic pressure losses. So to the end, you can boost the oil productions. That's actually the problem here. And what we are gonna do here is basically trying to maximize the revenue of oil production and minimizing the cost of gas lift, while taking into account the constraint that we have here. The first constraint is the total resources, which is the total gas lift rate, and total produced gas, because we might have, or usually we have, maximum capacity of your gas processing facilities. So we also consider a parameter that is time varying here. We consider it the gas oil ratio, and you can see it as a disturbance, or to be specific, it can be categorized as the fit disturbance. And then we implement our presented method and compare it with the ideal optimum solutions. We use model-based gradient estimation to estimate both cost and constraint gradient, and we use PI controller for each local system to drive the estimated gradient of Lagrange to 0. As a result, we can see that the performance of DFRTO can optimally allocate the shared resources in distributed manner without the need to solve numerical optimization problems. As expected, this method will have dynamic valuations issues, especially in active constraint switching, that can be clearly observed in the figure. If we take a look at a bit more detail, we realize that these dynamic valuations happen because the central constraint controller does not provide optimal shadow price immediately as shown in figure D. So there is some iteration that you need to do to get the optimal shadow price. Figure C shows that our PI controllers works well in driving the estimated gradient. By doing so, and by updating the shadow price, we can optimally allocate the resources, which is in this case is the gas lift rate. So as a conclusions, we have shown that we can convert dual decomposition framework or dual problem in general into a feedback control problem. In this framework, we update the Lagrange multiplier to control the constraint, and it enables system-wide optimal operations. Finally, as we only have now a feedback control problems, then we can avoid the need for solving numerical optimization online. This ends my presentations, and I would like to say thank you for all of you who has spent your time and attention for my presentations. Thank you for listening.